Hi guys, so hopefully you've had a go at these KC questions, which I set you to do earlier. So let's just get straight into it. A chemist investigates the equilibrium reaction between sulfur dioxide, oxygen, and sulfur trioxide, shown below. So here we've got our sulfur dioxide, oxygen, and sulfur trioxide. The chemist mixed together sulfur dioxide and oxygen with a catalyst. The chemist compresses the mixture to a volume of 400 centimeters cubed. The mixture is heated to a constant temperature and is allowed to reach equilibrium without changing the total gas volume. And we've got the equilibrium mixture contains 0.0540 moles of sulfur dioxide, 0.0270 moles of oxygen. At the temperature used, the numerical value of Kc is this. They've in fact here given us the units for some reason. It might not have been in the original question, but you know. So anyway, Kc is product over reactants to their corresponding powers. So sulfur trioxide squared divided by sulfur dioxide squared and oxygen not squared, which gives us units, gives us moles per decimeter cubed squared divided by moles per decimeter cubed squared moles per decimeter cubed. These squared ones can cancel each other out, giving us 1 over moles per decimeter cubed. When we turn them the other way up, then that becomes moles to minus 1 decimeters cubed, or the other way around. Okay. So determine the amount in mole of sulfur trioxide. Now, they have been slightly sneaky here. Do note that these are moles, not concentrations, so we'll have to bear that in mind when we come to do our calculation. But fundamentally, we're going to rearrange this so we get that sulfur trioxide is equal to the square root of Kc times by the concentration of SO2 squared, concentration of O2. So our concentration of SO2 is 0.054 divided by 0.4. The reason that it's 0.4 is that our volume is 400 centimeters cubed, so that's 0.4 decimeters cubed. If we just whack that into a calculator quickly, we get 0.054 divided by 0.4 gives us 0.135. Our concentration of oxygen is equal to 0.0270 divided by 0.4. So 0.027 divided by 0.4 gives us 0.0675. So if we now whack that in here, we've got our sulfur trioxide even is equal to the square root of 3.045 times 10 to the power 4 times by 0.135 squared times by 0.0675, and if we plug all of that in, 3.045 times 10 to the power 4 equals that, times by 0.135 squared equals that, times by 0.6. There we go, and then we are going to square root that, giving us our answer of 6.12039299. We're now needing to convert this from a concentration into a number of moles. So our number of moles of SO3, well, if we used N equals C times V over 1,000, we're going for this. So we've got 6.120399, I won't bother rounding it yet, times by 400 divided by 1000. So times by 400 divided by 1000, giving us an answer of 2.448157. Now we need to work out what an appropriate number of significant figures is. So this is 1, 2, 3. This is 1, 2, 3. This is 1, 2, 3, 4. So our lowest number of significant figures is 3, so we need to give this to 3. So 2.45 moles. Okay. I'll put the mark scheme up here in a second. So this time we've got ethine gas. Is manufactured in large quantities for a variety of uses. Much of this ethine is manufactured from methane, as shown in the equation below. Write the Kc expression for this. So we've got Kc is equal to the concentration of hydrogen to the power 3 even, times by the concentration of our ethine even, divided by our concentration of methane squared. That's it. That's all we were wanting. So we now have a research chemist investigates how to improve the synthesis of ethine from methane at a high temperature. The chemist adds methane to a 4.00 decimeter cubed container. The chemist heats the container and allows equilibrium to be reached at constant temperature. The total gas volume does not change. The equilibrium mixture contains 9.36 times 10 to the minus 2 moles of methane, and it contains 0.168 moles of our ethine. Calculate the amount in mole of our hydrogen. Now, I know that this is all a little bit not the largest amount of space, but I'm going to do this on another piece of paper, and I'm going to do this as a rice table again, because actually that's going to let me work out this next one. So rice, which remember was reaction, initial number of moles, change, an equilibrium number of moles, which will need to turn into concentrations later. But our reaction is 2CH4 in equilibrium with CH2, C2H2, and 3H2. Now, we don't actually know our initial numbers of these, or we don't know our initial number of this. We know that they've added methane to it, so we know that our initial numbers of moles of our ethine and hydrogen must be 0. We are told that this is 9.36 times 10 to the minus 2, and that we've now got 0.168 moles of this. We now just need to think about, okay, so that means that this has gone up by 0.168. The molar ratio between our ethine and our hydrogen is 1 to 3, so this is going to be 3 times that. Which is a slightly annoying number to just pluck out of my head. So let's just plug that into a calculator, make sure I don't do my mental maths wrong. So 0.168 times 3 means that this is going to have gone up by 0.504. So 0.504. We can actually skip ahead now, because we've actually calculated the amount in mole of hydrogen in our mixture. That was our 0.504, because it's 3 times that. And actually we can in a second answer this question as well. So if this has gone up by 0.168, that means that this must have gone down by double that, because it's 2 to 1. So 0.168 times 2 is, that's gone down by 0.336. And now we've got enough that we can work out what it was initially, because of course it must be that 9.36 times 10 to the minus 2 plus what it has gone down by. So we're going to add to this 9.36 times 10 to the minus 2. So we started off with 0.4296 moles of methane, and we're just wanting it in moles here, so that's fine. So we've got 0.4296. We're not asked for it to an appropriate number of significant figures or anything, so that is fine. Now we just need to turn these into concentrations. So we need to have a little look, and it was a 4 decimeter cubed container, so that means that we are 9.36 times 10 to the minus 2 divided by 4. 9.36 times 10 to the minus 2 divided by 4 is 0.0234. We're then going to need to divide that by 4, so 0.168 divided by 4 gives us, let's write it in, 0.168 divided by 4, so that's giving us 0.042, and then we're going to do 0.504 divided by 4, 0.504 divided by 4, giving us 0.126. We're now at the situation that we can plug it into our expression, because we're being asked calculate what Kc is. So let's plug it into our expression and make sure we put things in the right place. So Kc is equal to, I'm just going to rewrite it here so that I'm not going to make a little mistake. So it's the concentration of hydrogen cubed times by the concentration of our ethine divided by the concentration of our methane squared. So that gives us 0.126 cubed times by 0.042 divided by 0.0234. So if we plug that in, Not 0.126. I do have a cubed button. Times by 0.042 gives us that, divided by 0.0234 gives us this. So we get a value of 0.00359. No, we don't, because I forgot to square this number down at the bottom. I did make a mistake. So let's do that again. 0.126 cubed times by 0.042 divided by 0.0234 squared gives us that. Sorry, that's better. 0.153 43. That'll do. Now let's have a little look. So we're to 3 significant figures, so 0.153, and our units, well, our units are moles per decimeter cubed times by moles per decimeter cubed divided by moles per decimeter cubed squared. So squared cancels out that one, and that cancels out one of those. So we're now left with moles per decimeter cubed squared, which is moles squared decimeter cubed to the minus 6. So moles squared decimeters cubed, decimeters to the minus 6. Okay, let's get rid of that. So, the chemist repeats the experiment 3 times. In each experiment, the chemist makes one change but uses the same initial amount of methane. Complete the table to show the predicted effect of each change compared with the original experiment. Only use the words greater, smaller, or the same. So, the container is heated at a constant pressure. Now, this is where we need to have had a look at this. So it's plus 377, so that means that it's an endothermic reaction going forwards. So that means that if we increase the temperature, the equilibrium will shift to the right-hand side. And that means the number for Kc will go up because we're doing more divided by less. So this is going to be greater. And the equilibrium amount of ethyne, therefore, is also going to be greater. And the initial rate, well, we're heating it up, so we would expect it to be going faster, so this will be greater. A smaller container is used. So, Kc, the only thing that changes Kc is temperature, so this is going to be the same. The equilibrium amount of our C2H2, so we're using a smaller container, that means that pressures would go up, and increasing the pressure will favour the side with fewer moles. So we've got 2 on the reactant, 4 on the product, so this is going to be smaller because our equilibrium will have shifted to the left. But we're doing it under more pressure, and more pressure increases the rate of the reaction, so the initial rate would be greater. Catalyst is used at the start. Catalyst doesn't affect Kc, so this is going to be the same. It also doesn't affect the position of the equilibrium, so that's going to be the same. But of course it does increase the rate of reaction, so this is going to be greater. There we go. Question 3. Big old question here. So, a chemist investigated methods to improve the synthesis of sulfur trioxide from sulfur dioxide and oxygen. The chemist mixed together 1 mole of sulfur dioxide and half a mole of oxygen with a catalyst at room temperature. Compressed the gas mixture to a volume of 25 centimeters cubed, allowed the mixture to reach equilibrium at constant temperature and without changing the total gas volume. And we're then told that at equilibrium 82% of the sulfur dioxide had been converted into sulfur trioxide. Determine the concentration of sulfur dioxide, oxygen, sulfur trioxide present at equilibrium and calculate Kc for this. And you'll notice at the bottom that we're asked for the units as well. So this is where we're going to need to use our Rice table. We've got 2SO2 plus O2 in equilibrium with 2SO3. We'll make it into an actual table. We were told initially we had 1.00 moles of this and 0.500 moles of this, and we had 0.000 moles of this. The question is, what's the change? Or what has changed? Because they've not given us a nice easy equilibrium number of moles. What they have said is that 82% of the sulfur dioxide has been used up. So 82% of this has been used up. So if you worked out what 82% is, well, it would be 0.82 moles. So this is going to have gone down by 0.82 moles. So we're only going to have 0.18 moles remaining. We're going to have 18 moles of that left over. Again, now, just as we usually have, we needed to use our molar ratios. So this is 2 to 1, so we'll have used up half of that. So this will have gone down by 0.41, giving us 0.09, I suppose. and this is going to have gone up because this is 2 to 2, so this is going to have gone up by 0.820. So this is now 0.820. These are equilibrium number of moles rather than concentrations, so we're going to need to turn it into concentrations. Now we need to have a little look. So it's 25 centimeters cubed, so that means that our volume is 0.25 decimeters cubed. So we're going to do 0.18 divided by 0.25, 0.09 divided by 0.25, and 0.82 divided by 0.25, which should give us 0.18 divided by 0.25, so basically 4 is 0.72. 0.09 divided by 0.25 gives us 0.36, and 0.82 divided by 0.25 gives us 3.28. So Kc is equal to sulfur trioxide squared divided by concentration of sulfur dioxide squared multiplied by the concentration of oxygen, which is 3.28 squared divided by 0.72 squared times by 0.36. So 3.28 squared divided by 0.72 squared times by 0.36 gives us a number of 57.647. They haven't told us to do it to an appropriate number of significant figures, but we might as well. So we've got 1, 2, 3 significant figures, 1, 2, 3 significant figures, 1, 2, 3 significant figures, 1, 2, 3 significant figures. So we might as well do it to the same. So 57.6. And our units, well, moles per decimeter cubed squared divided by moles per decimeter cubed squared times by moles per decimeter cubed. Those two cancel those, giving us 1 over moles per decimeter cubed, which gives us moles to the minus 1 decimeter cubed. Like so. So, explain what would happen to the pressure of the system, as the system was allowed to reach equilibrium. We need to have a little look. So, we are going from, 3 molecules of gas on the left-hand side to 2 over here. So that means as these are consumed producing that, our pressure is going to decrease. Yeah, because we've got fewer molecules. Present. Yeah. If we were going from, say, 2 to 3, then our pressure would increase because we're producing more and more moles. Yeah. So we've gone from 3 down to 2 moles. So, the value of Kc for this equilibrium decreases with increasing temperature. Predict the sign of the enthalpy change for the Ford's reaction. State the effects of the equilibrium yield of SO3 of increasing the temperature at constant pressure. So, value of Kc decreases. That means that we're shifting to the left-hand side because we're products over reactants, so it's getting a smaller number divided by a larger number. That means that by increasing the temperature, We've done the opposite. We've gone back to the left. So that must mean that this is an exothermic reaction. We remember that exothermic reactions are negative. Negative. I'll go back to writing in black. And that would mean that this would decrease. Yeah, because we've shifted to the left. Okay. So the chemist repeated the experiment at the same temperature with 1 mole per decimeter cubed of sulfur dioxide and an excess of oxygen. The gas mixture was still compressed to a volume of 250 centimeters cubed. State and explain in terms of Kc how the equilibrium yield of SO3 would be different from the yield in the first experiment. So we're doing it at the same temperature. So Kc has not changed. Yeah, so the value of Kc hasn't changed, but we're going to have a larger number of moles of oxygen present at equilibrium of oxygen. And we remember, hopefully, from AS that increasing the concentration of a substance forces our equilibrium to shift to the opposing side. And of course, we do have sulfur dioxide present at equilibrium, so it can continue to shift. So we would want to say something like that the concentration of oxygen at equilibrium has increased. That means that so equilibrium has shifted left, right. Giving a greater equilibrium yield of sulfur dioxide, which means that the top of Kc expression is larger than before. Yeah. So that must be what has happened, because Kc is not allowed to change. So the only reason that it's going to shift it that way, or numerically, if we're thinking about it, that must mean that because our equilibrium is further over here, this is now a bigger number than these are together, bringing us back to Kc still being 57.6. Explaining it in terms of Kc is a bit complicated. You'll need to think about how the top is changing compared to the bottom. So a couple more. 2 more questions. Apologise, I seem to have gained a cough for some reason. I'm hoping that it's not COVID related. So iodine I2 is a grey-black solid that is not very soluble in water. Equilibrium 1 is set up with the equilibrium position well to the left, so it's mostly iodine still there. Solid iron is much more soluble in an aqueous solution of potassium iodide than in water, and equilibrium 2 is set up. So we've got iodine and iodide ions giving us I3 minus ions. A student dissolves iodine in potassium iodide. The resulting 200 centimeter cubed solution contains 4.00 times 10 to the minus 5 moles of iodine, 9.404 moles of I minus and 1.96 times 10 to the minus 3 moles of I3 minus ions. Calculate Kc for the equilibrium 2, give your answer to an appropriate number of significant figures. So this is sort of somewhere in between. The reason that it's a little bit tricky is that they've given us in moles instead of concentrations. So really we need to work it out as concentrations. But the first point is as it always is, so Kc is equal to the concentration of I3 minus, and it's not to the power of anything because there's only one of it, multiplied by the concentration of iodine, multiplied by the concentration of iodide. And of course we've got concentrations because this is an aqueous solution. So I'm just going to do this up here. So the concentration of I2 is equal to 4.00 times 10 to the minus 5 times by, no, divided by 0.2. So we have, and the reason that it's 0.2 is that that's how many decimeters cubed we've got. So volume equals 200 centimeters cubed divided by 1,000 equals 0.2 decimeters cubed. So doing moles divided by volume. So 4 times 10 to the minus 5 divided by 0.2 gives us 0.0002. Yeah. We then have 9.404 times 10 to the minus 2 equals that, divided by 0.2. So our concentration of I minus is 9.404 times 10 to the minus 2 divided by 0.2, which was 0.4702. And our concentration of our I3 minus ions is 1.96 times 10 to the minus 3 divided by 0.2. 1.96 times 10 to the minus 3 divided by 0.2 is 0.0098. So those are the numbers we're going to substitute in. So this was our I3 minus, so 0.0098 divided by 0.0002 times by 0.4702. So we'll do 0.0002 times by 0.4702, giving us a number of 104.2109. We can just do a quick little check to see whether that makes sense. This is a very low concentration. This is quite low, but it is higher than the I3 minus, but that is substantially greater than the concentration of our iodine. So it makes sense that our equilibrium is reasonably across to the right. Of course, we were told to an appropriate number. So 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, and 1, 2, 3. 3 significant figures is the smallest number of significant figures, so we're going to give it to 3 significant figures, so 104. And then our units, we're going to do moles per decimeter cubed divided by moles per decimeter cubed times by moles per decimeter cubed. Cancel, cancel, giving us 1 over moles per decimeter cubed, which is moles to the minus 1 decimeters to the power 3. So moles to the minus 1 decimeters cubed. I appear to have not managed to, on my copy, get this part of the question onto the next page. Hopefully on your sheet I have noticed that already. So the student adds an excess of aqueous silver nitrate to the equilibrium mixture. Predict what would be observed. Explain the observations in terms of both equilibrium 1 and equilibrium 2 and any species formed. So we hopefully know that silver nitrate is used for identifying halide ions. We of course have a halide ion here. We've got our I minus. So we would expect to see the precipitate formed, and it would be a yellow precipitate. And that would be because we've got our Ag plus ions reacting with our iodide ions to create AgI, which is a solid, of course, from our aqueous species over here. So, yeah, we would expect to make sulfur iodide. That means that we would get to see a yellow precipitate. If we have a little look then, we would expect, so what we're doing is we're removing iodide ions from our solution. That means that, sorry, I'll move this here. So we're removing these. So this is going down because we're turning them into solid silver iodide. That means that our equilibrium is going to shift to the left to try and recoup that. As a knock-on effect, that means that the concentration of iodine is going to increase. So this is going to increase, and that means that equilibrium 1 will shift to the left as well. What we would visibly see from that, so observations, is we'd expect to see more solid iodine because equilibrium 2 shifts to the left and equilibrium 1 shifts to the left. So we would say that equilibrium 2 to the left and side, and then therefore equilibrium 1 shifts to the left hand side and see more solid iodine. Yeah, or it dissolves less, or something like that. Right, last one. Last one. Nitrogen monoxide, NO, and oxygen, O2, react to form nitrogen dioxide, NO2, in the reversible reaction shown in equilibrium 18.1. There we go. Write an expression for Kc for this equilibrium and state the units, so it's product over reactants. So it would be concentration of NO2 squared divided by the concentration of NO squared, concentration of O2. For units, that's moles per decimeter cubed squared divided by moles per decimeter cubed squared, moles per decimeter cubed. Hopefully you can see where this is going. We've seen this exact situation a number of times. Those cancel out with each other, leaving us with 1 over moles per decimeter cubed, which means that we are moles to the minus 1 decimeters to the power of 3. The chemist mixes together nitrogen and oxygen and pressurizes the gases so that their total gas volume is 4 decimeters cubed. The mixture is allowed to reach equilibrium at constant temperature and volume. The equilibrium mixture contains 0.40 moles of nitrogen oxide and 0.80 moles of oxygen. Under these conditions, the numerical value of Kc is 45. calculate the amount in moles of nitrogen dioxide in the equilibrium mixture. I think when they say that they're mixing nitrogen and oxygen, they actually meant nitrogen oxide and oxygen. So, we're needing to turn these nitrogen oxide and this oxygen into concentrations so that we can use them in this expression. So, concentration of NO is 0.40 divided by 4, which is 0.1. And our concentration of oxygen is 0.80 divided by 4, is 0.2. So that means that, now if we rearrange this, we're working out the amount in moles of nitrogen dioxide, so we're needing a nitrogen dioxide concentration, so NO2 equals the square root of Kc times by the nitrogen oxide times by oxygen, which is the square root of 45, sorry, I missed a square on there, times by 0.1 squared times by 0.2. So let's just plug that in. So 45 times 0.1 squared times by 0.2, and then we're square rooting that, so we end up with 0.3. But that's our concentration. We need it in number of moles, so N equals C times V over 1,000, or C times V. So our number of moles of NO2, because of course we've been told our volume in decimeters cubed anyway, is 0.3 times by 4, which is 1.2. That's it. That's done. Okay. So I know I only have one rice question in there. I will work on providing you with a couple of others. But you can see the way that they're sort of shuffling it round rather than just straight up going, okay, give me the expression. Okay, here are the concentrations. Work it out.